All right, welcome everybody to ArcGIS Runtime Analysis. My name is Lucas Danziger. I'm the product owner of the Runtime SDK for Qt team. And we've got Mike right here. He's the product owner of our .NET SDK. So we are going to be talking about analysis, and this is a cross-runtime session. So even though you'll see some code in one language or another, these concepts apply to all of our different SDKs, and we can do that because we share a common core architecture and design. So in the yellow here, you can see some of the other cross-section sessions, and we also have some product-specific sessions. If you really want to sink your teeth into Java or .NET or C++, we have sections on that as well. So that's a theme that we have throughout. So today we're going to be focusing on just analysis, and we have a few different areas of analysis within the runtime. We're going to first talk about geometry operations. That's kind of at the core of everything. And then Mike is going to go through geoprocessing and visual analysis. Okay, so geometries. Like I said, geometries are at the heart of GIS. It's really what defines where all of our different vector data is drawing. But it also means that we can do analysis with that vector data. And we do that analysis with a class called the geometry engine. The geometry engine is available in all of our SDKs. And what it is it's a class with a bunch of static methods that take in geometries. Input geometries can be point, line, polygon, envelope, or multi-point. And when we're talking about geometries, they can be coming from anywhere. They can be created programmatically, or you can be getting them from features. When we say feature, we're talking about geodatabases and feature services, geo packages, and graphics are the temporary display elements that we see on the map view or scene view. Those need geometries as well. These are fast and they're synchronous client-side processing. So this doesn't send anything out to the server. It's synchronous. The only reason we made them synchronous is because they're extremely fast and it makes it a little bit easier to work with without really any performance penalty. And there's three different groups of functions with the geometry engine. There's geometry dimension operations, there's geometry spatial operations, and then there's operations to help build new geometries. So let's dive into each of those. The first is geometry dimension questions. These are questions like, how long is this line? What is the area of this polygon? What is the boundary of the polygon? Or what is the distance between point A and point B? So in this case, we've got some Java code. This is the geometry engine distance between function. It takes in a point, 2 points. We've got point A and point B in this case, and it returns a double. So it's very simple. Again, it's static. Notice it's calling on the class and not an instance of the geometry engine. And some things to keep in mind are that the results are always in the spatial reference, the unit of the spatial reference. So if you're working with Web Mercator, for example, that's in meters. So your results will be in meters as well. Also, all the geometries that are fed into the geometry engine must be in the same spatial reference. So for example, if you're working in a map that's in Web Mercator and you're getting a point from your click, it will probably be in Web Mercator as well. But if your data from your feature layer is in some local state plane, you're going to need to go ahead and project that. So we have a method on the geometry engine called project. And you can basically pass in that point into the project method, and you pass in a spatial reference object of the spatial reference that you're targeting, and that will return a new geometry that is in that spatial reference. Now by default, we will pick the geographic transformation for you in the case that your datums differ, but we also now support you specifying which transformation you want to use. We pick the best one based on where your data is located and the two different datums that you're using, but sometimes people need to specify that on their own. So the next bit of functionality in the geometry engine is answering questions about geometries. For example, does this geometry, this polygon, contain this point? Or does this line cross this polygon? Or does it intersect it? what's the nearest vertex, or do they overlap each other? Does point A touch point B? Is this point within this polygon? So you can think of a lot of different use cases. Geofencing is a big thing. You want to know once you enter an area, you've got your point as your location and you've got your area of interest as a polygon. Whenever your location changes, you can call a method to basically check, am I within this? And the third group is creating new geometries based on existing geometries. So everybody's favorite analysis is the buffer, right? You drop a point and then you give it a distance and it makes the buffer around that point. You can also do it around lines and polygons. We've also got the union. So the union basically takes two geometries and unions them together as one. We also have the intersect, which gives you a new geometry based on the parts of the input geometries that intersect each other. And then the opposite is the difference. So that's a new geometry based on what's not common between the two input geometries. Plus, we have many more. For example, if you wanted to know where to label a point, you can use the geometry engine to find the optimal place to place a label. So the important thing to note here again is that these are all geometries. If anyone's familiar with geoprocessing, which Mike will talk about in a little bit, that's performing at a layer level. It's doing it for you against everything in that layer. Geometry engine requires you drill down to the individual geometry. All right, so let's look at a couple of these in action. So this is the Runtime SDK for Qt sample viewer. All of the different SDKs have these samples. This just happens to be the one that I'm using. So I'll drill into the geometry section, and the first one I'll take a look at is the buffer. So as I click here, you can see that we are drawing a buffer of 1,000 miles around the click point. But one thing that's kind of interesting about this sample is that as I go further north, you see that the red buffer is actually getting bigger. That's because this is a geodesic buffer, and the blue-purple one is a planar buffer. So the geodesic buffer takes into account the curvature of the Earth. So it's a more accurate representation. It's bigger, similar for the reasons that Greenland looks so huge on the Web Mercator map. So it's important here to know if you want to be using a geodesic or planar. Like if you're working in a state plane zone at a certain scale, it might make more sense to use a planar. Here we have the clip geometry. So we have the state of Colorado outlined and then a few different polygons. And I click the clip button and it clips that polygon into a multi-part polygon. This example shows Lake Superior. It's very generalized. And then we have a rough line that's indicating the area, the boundary between Canada and the United States. So let's say we wanted a new geometry that represented, two new geometries, one that represented the section within the United States and the section within Canada. We can pass that into the cut method, and that will cut it in half. So you can see it's very fast. Like I said, it's synchronous and it's very fast. And the last one I want to show is the spatial operations. We have two polygons in this case. One has a donut hole in the middle, and the other one, the blue one, is just solid. I can union the two together, and that gives me a new output. The new output is all red. That's one geometry now. Or here's a good example of the intersection. The red part is the part that intersects each other. So this is what's common between those two geometries. So those are the different geometry engine samples I wanted to share with you. And with that, I'll pass it over to Mike, who's going to talk about geoprocessing and visual analysis.
All right, thanks, Lucas. So let's take a look at geoprocessing. Lucas already contrasted geometry engine with geoprocessing, where geometry engine deals with specific granular geometries, and you're providing those via the API. Geoprocessing essentially deals with content at a layer level. You can obviously use queries to get subsets of content from that layer to use in your geoprocessing. But we'll take a look at what the framework is and then think about how we work with that in terms of the ArcGIS Runtime API. So the geoprocessing is a framework within ArcGIS. So it's a framework and it contains tools for processing spatial data. There are kind of two different forms of geoprocessing. One is about spatial analysis, such as buffer, intersect, and viewshed. And you can see Lucas mentioned a buffer within Geometry Engine. We have a buffer within geoprocessing as well. And really the buffer within the Geometry Engine would be far quicker for individual geometries. But within geoprocessing, you might use that in combination with multiple different tools there. Geoprocessing also can be used for data management, creating new feature classes, adding fields to that data, adding a domain to a field as well. So spatial analysis and data management. ArcGIS Desktop comes with more than 1,200 built-in tools, as does, so that's across, true for both ArcMap and ArcGIS Pro. And you combine those into custom tools and workflows, either using Model Builder, so a visual canvas that you can drag and drop tools onto and connect those together into a workflow, or you can write your own Python scripts for kind of finer-grained control over that geoprocessing. You either publish those to ArcGIS Enterprise as services, or you can make them available offline as local services with the ArcGIS Runtime Local Server. So that's really where geoprocessing kind of comes into the ArcGIS Runtime, is you can use services both online with ArcGIS Enterprise, or you can use local services with the ArcGIS Runtime Local Server. So just to kind of re-emphasize that framework then, there are ArcGIS tools, so built-in tools that are out of the box within ArcGIS, or there are custom tools that you create within Model Builder or within a Python script. So there are some conditions for publishing geoprocessing services. You have to run the tool within ArcGIS Desktop before publishing. So what that does is it validates the inputs, it validates the processing, and it generates valid outputs as well. So essentially guarantees that you have a valid geoprocessing workflow, and then it can be published. You can publish the result to ArcGIS Enterprise as a service. That includes the input data, the output data, and any project data. So you need to think about where that data is located and what the size of that data is. The ArcGIS Runtime API provides types to represent a geoprocessing service. So that's a task within the API. And also then specific requests to run instances of that task, and those are jobs. So the API contains a geoprocessing task, and the specific executions of that task are called jobs. You build up the parameter objects, you send those to the service, and you await the results. And then you process the output parameters, and they could be a variety of different content types. Once we start talking about local services within ArcGIS Runtime Local Server, that contains a subset of the tools that are available within ArcMap and ArcGIS Pro. So approximately 500 tools. If there are tools that aren't listed in the documentation, just please get in touch with us and we can look at adding those tools to the ArcGIS Runtime. The tools have to be packaged, so you create a geoprocessing package. That's either a GPK file from ArcMap or a GPKX from ArcGIS Pro. That package includes all the data required for the execution of the tool. So the input data, project data, and output data. So again, you need to think about what that data is, where it's located, and how that will be packaged in terms of the eventual data volume. The local server API within the runtime kind of makes you a mini server administrator, if you like. So you're responsible for starting local services and then connecting the geoprocessing task to that, and then ultimately stopping that local service as well. So just to re-emphasize the workflow then, using Model Builder or Python, you create a custom geoprocessing workflow, either in ArcGIS Pro or ArcMap. That creates a service definition if you're going to publish to your enterprise GIS server, or a package if you're going to use that in conjunction with the ArcGIS Runtime Local Server. So a few tips then for building geoprocessing tools. Keep the input data and output data small. So remember, when you run that model or script the first time, you're essentially just validating the workflow. So the idea is keep the input data and output data small, because that will get packaged up within the package. Use data that's local to the GIS server or local server, so you're not incurring the overhead of connecting to a network. Write any intermediate data to memory. So if you have small intermediate data sets that are just temporarily required for additional processing, you can use an in-memory workspace, and that will just get cleaned up after the processing. So it avoids the overhead of writing to disk and reading from disk. You should add attribute and spatial indexes to your data, so that improves the performance. Avoid any unnecessary coordinate transformations. So that they can happen, but every time you do a transformation, it incurs an overhead in the processing. So if you can avoid those by pre-processing some of your data or ensuring it's all in the same coordinate system, then that's recommended. Reduce the data size. So perhaps one part of your geoprocessing workflow takes a subset of the data, and then the processing only operates on that subset of the data. Okay, so let's take a look at geoprocessing. So here we've got a base map using the topo map, and what I'm going to do is draw a line across the terrain here, and that's being sent to the ArcGIS Runtime Local Server, and it's creating an elevation profile. So you can see that took a few seconds to run to draw to calculate the elevation profile. There's a couple of extra things here. As I'm hovering over the line, we're actually getting the distance from the start. So let's take a quick look at how I built that. It actually started with a Python script. So here I am in Notepad writing some Python, and we can see the first input is the line. So the line that I drew on the map view there, using the API, I passed that into the local geoprocessing service as a geometry. I also passed in a string that represented the path to the raster on disk. So there were two inputs, the line and then the raster. I'm using that in-memory workspace to create a couple of outputs just temporarily during my processing. I used the 3D Analyst Interpolate Shape tool. So based on the raster, the line, and then my temporary in-memory data set, that's going to interpolate that shape and add Z values to all the vertices. And then I'm also using a linear referencing tool, create routes here, and that adds the measure value onto each of those vertices for the distance along the line. And then finally just set the parameter at the end. So within ArcMap or within ArcGIS Pro, I then need to run this script, provide the valid inputs, allow the processing to run, and then create a valid output, and then I can package that as a physical file, as a geoprocessing package. Then within Visual Studio, here's that piece of code that I talked about where you're a mini server admin effectively. So I create a new local geoprocessing service, and I pass in the path to a GPK file that I created within ArcMap there. And then the code beyond there essentially creates a geoprocessing task, provides the input parameters. That processing happens locally on the ArcGIS Runtime Local Server, and then returns the result to me. Okay, so what I'd like to do now is contrast geoprocessing with interactive visual analysis. So within the ArcGIS Runtime, we provide a number of different visual analysis tools. The available tools are line of sight, Viewshed, and location distance measurement. These are very fast GPU-based operations, and the crucial point here is they act on the current visible resolution of the data. So when I was running that geoprocessing operation and I drew a line across the terrain, that was acting on the full resolution of the data set that it read from disk. When I'm using these visual analysis tools, they're only acting on the resolution that's available within the display at the time. So it depends on the actual zoom extent, or the extent that you've zoomed in towards the terrain. So these are really kind of exploratory, investigative tools for getting a good picture, but it's not necessarily about persisting results on disk. I actually just lost my internet connection, so my local server demo worked great because that was running on my local machine. I can't show the demo that has some content in the background. Okay, Lucas can show it. Ready?
Yeah. You want the line of sight?
Yeah, do line of sight.
Yeah. Does this one work? Okay, so this one has a line drawn. This is in the Patagonia mountain range in Argentina. And as I click, you can see that the line is two different colors. That's because the cyan color is visible. Picture a start point and an end point. From that start point, only this cyan color is visible. If I click over here, the whole line is visible, but there's this big ridge right here. So as I click, that's now magenta. I think I can even, here we go. So I'm doing a click and drag, and you can see how fast it's updating on the scene.
Nice. Thank you. And actually, just another example. There's an observer, which is the red buller there, and there's a line of sight running to this vehicle that's moving around the outside. So you can see the speed of the update as it becomes visible and not visible. So the interactive visual analysis for line of sight then determines the visible and not visible portions of that line between the target and the observer. The output is a line graphic symbolized by the visible and obstructed areas. The key is that you don't have access to that graphic to persist that anywhere. It's literally just displayed within a scene overlay. And then there's a number of different types of line of sight analysis. And then another key point is you get events triggered when the target is visible or not visible. So the other interactive visual analysis that I want to talk about quickly is Viewshed, that determines the visible and not visible portions of a surface based on an observer point. And again, extremely fast performance, GPU-based operation. And there's a number of different types based on whether you want to provide a map point as a location or a geo element. And the geo element is just a feature or a graphic. And then the third one is the location distance measurement. So that's actually an interactive measurement within the scene view. And you get, via the API, the results you get are the horizontal distance, the vertical distance, and then the actual diagonal distance as well. And those measurements are planar, so they're good over relatively short distances. Okay, so let's take a look at a quick summary then. ArcGIS Runtime enables spatial analysis in your apps. It's very common to actually combine multiple approaches that we've talked about today, geometry engine and geoprocessing, and then some element of visualization. They can be local to the device for offline workflows. A good example is when I lost my Wi-Fi connection there, but was able to use my ArcGIS Runtime Local Server for geoprocessing. Or they can run in your enterprise or the cloud. So when we did this last year, we talked about a roadmap for 2018. And we actually did all of these. We added more geoprocessing tools for local server. We added more 3D visual analysis tools, the 3D distance tool. And we improved package support with ArcGIS Pro and ArcMap packages for local server. If you want to know about the road ahead for analysis in the runtime for 2019, there's a session on Thursday afternoon in Primrose B. All right. Thank you very much for attending the session. Please take the survey on the app.